So thank you for having me today. Now, before I dive into the reactive amazing world of Vue, let me just briefly introduce myself. And yeah, hopefully this works. There is some slight delay because of the Chromecast, so please have patience. So as you can see, my name is Miroslav Jonaš. Underneath you have my Twitter handle and my GitHub handle, so feel free to follow me, tweet me, stalk me, fork me, whatever. I'm developer at 5G Systems, and I'm quite active in Angular community. I'm one of the co-founders of Angular Austria Association. So although some of you might know RxJS as closely associated to Angular, ReactiveX is actually way older than both Angular and RxJS. The reactive ideas first came out in 2009. They were implemented originally for .NET inside of Microsoft by this guy. His name is Eric Meyer, and you can also recognize him by this psychedelic t-shirts that he likes to wear. So he set up the whole theory around reactive programming. And this idea was really well adopted first in .NET, so it soon followed in other programming languages. So today now you have original ReactiveX implemented not only .NET, but also in Java, in Python, in PHP, in Ruby, Go, etc. So in most of the popular programming languages. And not only it exists as a part of this official ReactiveX, there are a lot of different libraries and frameworks that copy the same idea and have some slight differences. Some are more performant, some have some different operators than ReactiveX, but in shell they share the same idea. So let's see what exactly is ReactiveX. Now, before I give you more insights on what is ReactiveX, I want you first to tell me how many of you actually heard about RxJS, and no, it doesn't count if you just heard it a minute ago. So just raise your hands. Okay, and how many of you have actually used RxJS in their software? Okay, cool. So this might be interesting to you then. So there are a lot of definitions on ReactiveX. Some are a bit cryptic, some are circular, so they kind of explain itself by referring to itself. But one of the definitions that I like the most is that ReactiveX is a combination of the best ideas from three things. That's functional programming, iterator pattern, and observer pattern. Now, if some of these concepts are foreign to you, don't worry, because we're going to explain them one by one. So the first one is functional programming. Functional programming is actually style in programming, where you, instead of writing procedures, you show the logic of your code through a list of chained functions, where each function is pure function. Now, pure function means that function has clear input and clear output, and it doesn't have a state. So if you run the same function with the same input, it will always give you the same output. Also, the second important thing is that every function doesn't have side effects. So that means the function is doing exactly what it should. It takes the input, calculates somehow the output without changing something on the side. Now, maybe it's a bit easier if I explain how the functional programming works by showing what functional programming is not. And for this, we're gonna have our first eating metaphor for today. So on the slide, you can see one omelette. So we're gonna show how the typical scrambled eggs recipe looks like. I'm sure you all made scrambled eggs at least once in your life, but this is generally how every recipe looks like. So first you have some ingredients, you assemble them, they all have some different amount in which you need them. Then you have usually some mechanical processing of these ingredients, like chopping them, slicing them, mixing them, etc. Then there's a main cooking part where you actually process the ingredients, and finally your meal is done and you can serve it. Now, this recipe that you see on the screen is quite trivial, And most of the recipes are, but there is one thing that recipes usually don't expose, and that is what happens if you are dealing with some non-standard situation. So normally this is a recipe for one person. What would happen if you had two people, or if you have one person that is really, really hungry? Which part of these you have to double? So normally everyone who made ever in their life some scrambled eggs, they know that they need twice as much eggs if they want double portion, maybe twice as much salt, twice as much pepper, perhaps twice as much oil. But do we need two pans or two stoves? Now this question might sound trivial or stupid even, but imagine that this is not scrambled eggs recipe. Imagine that this is some super complex chemical reaction that you have no idea about. Would you still be able to confidently say which parts of this reaction have to be doubled or not? And accidentally, these are the questions that we ask ourselves every day when we implement something. What things can we parallelize? What can be reshuffled? How can we reuse some resources? What happens if there is an error? For example, if the electrical energy goes away, do we have to restart everything, or can we just continue making our scrambled eggs once the electricity is back? Of course, this is trivial for scrambled eggs, but for some things it might not be that trivial. So let's see how this would look like in a functional way. Now you can clearly see the hierarchy coming just from these linked functions. So we can see that we can only serve the meal once the steering has been done. And we can see that steering depends on the fact that the ingredients or our main meal has thickened. We can also see that the heating of the butter or oil in the pan can be done in parallel with the beating of eggs, salt, and pepper. So we can already see that which parts can be done in parallel, which parts can be shuffled, what are the kind of hierarchical dependencies between the steps. Now, if we consider that beating the eggs and stirring them can be kind of explained as just simply mixing the ingredients, then instead of this, we can just say that we have some stream of ingredients that we put in the pan, and we stir them until they have thickened. That would also mean that we can start with 2 eggs, and somewhere when we are halfway there, just add another egg and another egg. Of course, we will finish once everything has thickened, but as long as it's not done, we can still add ingredients. And this is what functional view on your development gives you. It gives you more insight what you can do and what you cannot do. Now, the next two patterns that we're going to describe are the original patterns coming by the proposal from Gango 4. For those of you who don't know what Gango 4 is, those are 4 authors that wrote a book back in the 90s. And the book is called Design Patterns, Elements of Reusable Object-Oriented Software. And although this book is more than 20 years old, the patterns that are described in this book are still quite relevant in today's development. Maybe not as much as they were relevant back in the days, but you can still use them, and you still use them in your daily work. So the first pattern that we're going to explain is Iterator pattern. Now, for this pattern, I want you all to imagine the best pizza in the world. Just imagine the best pizza you ate in your life. You can choose the toppings, you can choose the size, and imagine this pizza standing somewhere in front of you. Now, for those of you who don't like pizza, I have a bad news. Unfortunately, this is prerequisite to learn reactiveness, so sorry. Now, imagine the best pizza, and this pizza is already pre-sliced. You slowly approach this pizza. First, you look at it, and then you say, "Hey, pizza, can I have a slice?" And pizza replies, "Sure, go ahead." And you take the slice, and you eat the slice, and it's the best slice you ate in your life. But then you realize you're still hungry. So you come to pizza, and you say, "Hey, pizza, can I have another slice?" And pizza says, "Sure, take another one." And you keep taking one after another after another. At some point, you come to pizza, and the pizza says, "Sorry, there are no slices left." So this is, in short, how Iterator works. It gives you structure over a collection, and you can retrieve the items from this collection one by one. And it also tells you whether there are more items left. And it has, of course, some limited capacity. Now, if Iterator was kind of manual because you have to ask for each slice, the observer pattern works a bit differently. You subscribe once to the events, and you just wait for these events to arrive. Now, in order to explain this, I'm going to tell you a short story. When I was young, I was living in a small town. And being a small town, you couldn't just buy bread whenever you wanted. You had to register in the local market day before, and you had to kind of reserve the load of bread. Now, these breads would usually come between 7 and 8, which was time when my entire family would go to school/work. So we wouldn't be able physically to pick up our bread. And we didn't want it to stay there in the market for the half of the day. So a grandma who was living quite close to us, she would go in the morning, she would pick up a load of bread for them and for us. And then when I was coming back from school, I would stop by to take this bread. Now, this was usually around lunchtime, and I was, of course, at that point quite hungry, so I would normally have lunch at their place. Now, I would usually eat scrambled eggs, which I just told you about, but what my grandma was really, what her specialty really was making pancakes. She was really expert in making the best pancakes in the world. And what I would normally do, if I felt like eating pancakes, I would just come to grandma and I would say, "Hey grandma, I'm hungry, can you make some pancakes?" And then split second later, she would be standing next to the stove making the pancakes. And I would wait a couple of minutes, and then pancakes would start arriving one after another. And they would keep coming and coming and coming. And at some point, I would have to say to my grandma, "Hey grandma, stop, I'm full, I cannot eat anymore." This is how the observer works. So you subscribe to something, you wait for these events to arrive, and at some point you have to cancel your subscription, otherwise this will keep coming and coming and coming forever. Now, observer doesn't have to give you subscription over a collection of items. You can subscribe just to a single event. Just imagine if you're making HTTP call. This is usually a one-time event. So you subscribe, you get something back, and then your subscription is gone. There's nothing else coming back. Now, this is roughly two types of observables. So we have like one-time observables and observables that come in streams. And anything can be observable. The chair next to you, the person next to you can be observable. So any tangible or any item that you can think of can be wrapped as an observable. But there are also roughly two types of observables, hot and cold observables. Now, for those of you that know me, know that I'm a really big fan of sushi. And I could eat sushi, I think, every single day. And in Vienna, if you want to eat sushi, there are roughly two types of restaurants. The first type of restaurant is your typical restaurant. You come to the restaurant, you take a seat, then waiter or waitress approaches you, you take an order, you wait a couple of minutes, and your food arrives. Now, what normally happens is that this sushi does not exist before you come to the restaurant, so it was made, hopefully, fresh for you by the chef. And these are so-called cold observables, so they don't exist up front. Only when you subscribe to them, only then they are made or prepared for you. The hot observables would be so-called conveyor belt sushi restaurant or running sushi restaurant. These are the restaurants that have a track or a belt where the food is going in circle, and at some point of this track there are chefs making fresh sushi and putting it on the track, and all you have to do, you just come to this restaurant, you take a seat, and when food arrives to you, you take it out and you eat it, and then the next piece comes out, again you eat it, etc. So difference is that this sushi was made even before you came to the restaurant, and the chefs will most likely keep making this sushi and all the other pieces of food once you leave the restaurant. So this is, for example, taking a glass of water from the stream or from the tap. So this water is coming whether you take it or not. So you have to subscribe and you have to unsubscribe. In development, this would be, for example, click events or mouse moves. The user will move mouse whether you are listening to this event or not. Okay, so I explained a bit of HTTP calls and event handling. And for some of you, this might sound slightly like a promise. In fact, there are often cases where people are making HTTP calls and they are asking themselves, should I use promises or observables? And observables can be used instead of promises, but the big difference is that they are like advanced version of promises. So one of the differences between promises and observables are that promises are not cancelable. So once you make a call to the backend with a promise, this call will come back whether you want it or not. So you cannot cancel it once it's made. There are now some changes where the promises will be cancelable, but by definition, promises are not cancelable. Observables are cancelable. So if you imagine the situation in the restaurant, that would mean that with a promise, when you order sushi, you have to eat it. Or you don't have to eat it, but it will come nevertheless, and you have to pay for it. With observables, you can order, and then you can change your mind later. And you can still cancel that subscription or change it. The second thing is that promises are async by default, and they guarantee that they are async, so you can depend that the execution of the asynchronous callback will happen outside of the main context. Now with observables, it depends, depending on that, what you are wrapping in observable. So if you're wrapping something static in observable, the execution will happen synchronously, so it will happen in the main context. If you wrap something asynchronous, like call to backend, it will be async. There are some parts in observables called schedulers, which can change the synchronicity based on however you like, but this is a bit more advanced stuff. And one of the really good things that observables give you is they give you a lot of operators, which we will see soon, with which you can manipulate the data that's coming from the observable to change it before you pass it to your subscription. Now, there was quite some theory around it, but now let's see how this looks like in a code. So I have my demo gods aligned. Hopefully everything works okay. Okay, so we're gonna build a game. As you can see on the screen, this will be a Tetris game. At the moment, there's just simple Vue component. It's written in TypeScript, which might be a bit strange to you, but TypeScript, I personally prefer TypeScript over ES6 because it gives me a bit more intelligence and it allows me to code a bit faster, but it's just a preference. So you can still do all this stuff in normal ES6 or ES5 even. So as you can see, we have a component. Can everyone see the code, or should I enhance a bit? Well, the lights I can't really fix, unfortunately. Maybe we can kill one of these lights, if possible. So we have our mounted method, or mounted lifecycle hook, where you can see I just have a reference to this main element, which is actually canvas. I'm setting some width, some size, and then I'm passing the context of this canvas to the init game method, where I'm just printing out the text I want to be Tetris. Now, we will remove this, and instead, we're gonna put some code here. Now, I did some preparation up front, otherwise this would take a bit longer. So I can show you just quickly what's there. We have some constants, such as shape colors. So we want every block from Tetris to be in different colors so that we can nicely see what's going on. We have our keyboard keys, which we are interested in, like arrow left, right, down, and space for rotation. And I have the definitions for the board width, height, and cell size. The next thing I have here is game logic. Again, this is quite simple. Method to check if it's game over, to move block, to rotate block, to remove the full rows. Then there are some rendering methods for rendering the background, the board, the block. And then we have our shapes definition. So each possible shape is described with this matrix. We see the interface for the block. Every block has X, Y position. It has a shape, which is one of these shapes underneath. And it has colors to know in which color we should print it out. And finally, we have our main board. For those of you who have used Vuex or any other state management, this might be familiar. So we have a state. It's quite simple state. So our state consists of the board, which is what you see behind, and then the block, which is not yet merged with the board, so the block that's still moving. And then there are a couple of methods here, like choosing the random shape, random color, etc. And then we have short reducer or mutations, if you wish, which just generate the scene on init, on space rotate the block, on left, right, or down are just moving blocks. That's it. So it's quite simple. Now let's see how we're going to write this code. So one thing that game has to have is be able to use keys to navigate, right? So we're going to use from event, which is down. From event is a wrapper around DOM events. So what we are doing here is we are saying that for every, just subscribe, key. So what we are saying that for every key down event happening anywhere on the document, we are subscribing to it and we're gonna console log it. So now if I go to my browser here, let me just see if this thing is running. No. Maybe I should have done this first. This is some stale data. Okay. Oh, there are some leftovers here. Okay, so now it should be fine. And if we restart, and now if I'm pressing some keys, you might see that stuff is coming out here. So we see that every keyboard event is printing out. Now, we don't generally care about this big keyboard event. All we care about is just the code of the key event. So what we can do is, as I mentioned before, for the observables, there are a lot of operators which we can apply, and we apply them through the pipe. So we can pipe in the operators before we subscribe to it. So first one we're going to use is a map. This is the same thing as a standard array map. So we take our key. We're going to say that this is key is a keyboard event. And then we're going to map this event to event.code. And now if I save this, Now you can see that we no longer have the full event, we have just the key codes. Now, I showed you earlier that we are interested only in 4 codes, 4 keys, that's left, right, down, and space for rotation. So we would like to somehow get rid of these. We are not interested in all of them. So what we're going to do is, I have this keys object, and I'm going to say that I will map every event code into my key object. And now if I restart, now we can see that it's printing undefined for some of them, which is fine because it only prints for the ones we are interested in, but we don't want this undefined, that's kind of annoying. So we can filter out the stuff we don't need. So we're going to say return only the ones that have some value. So again, if I restart, and now I'm pressing some keys, but you don't see anything unless I press one of the keys that we're interested in. Now, that's the first part, listening to the keys. Now, the second part that every Tetris game has is that it has some flow. So whether we are using our keys or not, whether we are playing the game or not, the block will fall down. So what we want to do, we want to have some game pace. So we're going to create observable around interval. I'm going to pass this game speed that I have prepared, which I think is 500 milliseconds. And now if we subscribe, and we print it out again, let's see what this gives us. Now we can see some numbers printing out. So every half a second, there is one increased number coming out. Now, we don't want numbers. What we care about is the key downs, because what happens every half a second, the block will fall down one line. That's the same thing as someone just pressing down constantly. So we're going to map this again with our pipe. We will map whatever comes through to keys dot arrow down. And now you can see that instead of numbers, it's arrow down and it's increasing. Now we have 2 subscriptions that are doing roughly the same thing. They are printing our keys. So we want to combine this. As we mentioned, every observable consists of 2 parts, the thing that we observe and our subscriber that's observing. Now there's one more structure in the observable world, which is combination of those 2. It's called subject. So subject is both observer and observable. So it can listen to events from somewhere else, but it also emits the events it receives. So we're going to create const. Let's call it action. And we're going to say new subject. We don't know still what we're going to pass, so let's say any. And now, instead of subscribing to console log, we're going to pass here action. And the same thing we're going to do here. Okay, and now we can say action, subscribe, console log. Okay, now what we did now is we diverted the key press events and game speed events to the same action. So when you look at the result, it's actually the same. But what we can do now is we can use our next operator, which is called scan operator, and we're going to pass two things, our scene reducer function, and we will call generate scene. Okay, let me just import all of these. Okay, so scan operator works similarly like a reduce function on the array. So what reduce function does is it has some initial value, which in our case is this generate scene. And based on a collection, it will do constant recalculation, and at the end it will give you the end result. So hopefully everyone knows the reduce function in the array. So you have two things. One is the current value and then the accumulator, and in every step you accumulate the new value, you calculate the new value. Now the scan works similarly, but with one slight difference, and that is that reduce only gives you result at the end, while scan gives you result along the way. So every time we recalculate the new value, scan will spit out the current value. So it doesn't wait until the end, it will give you constantly values. So what this does for us is that every time the key is triggered, we will recalculate the scene and we're going to print it out. So now if we refresh this, you can see that instead of keys, we have our board and block printed out. Now this doesn't give us a lot, so let's print this out. So we say scene, and we're gonna say render scene. We need to pass our context and our scene. Now if I save it, we can get rid of this now. And now we almost have a full game. So you can see that you can use this, you can use the keys, just see how the... And now there's one thing still missing. So we showed now when game changes, how do we generate new scene, but we still haven't told it how to handle game over. So what we want is we don't want to calculate the new scene endlessly. We want to do it only until our scene is not in game over state. So this function that I have is game over, simply checks based on a scene if it's game over scene, if the block cannot be moved anymore. And our take while operator is simply telling us, take this observables or have the subscription as long as this is true. Now, if we restart this, we're going to see that although our observable has finished, we can't really tell because we didn't change anything. We're still just rendering the scene. So we don't know that rendering of the scene has stopped. So now we're going to use the things from our Iterator world. Now, if you remember the story about pizza, that was that our iterator pattern was giving us possibility to get the next item, but it was also allowing us to do something when there are no more items left. So we're going to say when our observable is complete, we're not going to render scene, we're going to render game over. Now if we restart, let's try to end it again. That's it. Now, one thing which might not be clear immediately is that observables still work in the principles of event subscription. And as you probably know, when you subscribe to some events, you might potentially end up with a bunch of subscriptions or listeners lying around filling up your memory. So what you want to do is, when the game is over, or when you close the component or leave the page, you want to get rid of this subscription. You don't want this to be hanging around in your memory and still listening to the key press events and this interval timer still running. So what we can use now, we can use our hookup before destroy. And we're going to create another subject, which we're going to call destroy subject. And we'll say that this is type void. It doesn't return anything. And on destroy, we're going to say that this destroy will fire a single item, and then we're going to complete this stream. So we are just firing one item, and we are closing it. And now what we want to do is we want to say this is fine for a take while until game is over, but if user leaves the page before the game is over, we want to say take until, and we're going to pass in our destroy object. So as long as you are here, everything will be fine, but as soon as user leaves, the before destroy hook event happens, which will then trigger this destroy subject, which will fire a single event, and this single event will close our action, and with action it will close the two subscription above. So that's all from the coding example. Now let's go back to the presentation. So hopefully by now you got enough information and enough motivation that you start experimenting yourself with RxJS and using it in your own solutions. You can see here a link to the original repo where you can see this whole code. If you go there next to it in one of my repos, you can see the same solution with Vuex. So you can compare VueRx and Vuex solution. Based on the lines of code, it's more or less the same, but you will clearly see that the Rx solution is more clear and gives you nice flow of the application, while Vuex at some point becomes overcomplicated with subscription to events and handling all the events listeners and detaching event listeners. Additional thing that exists in the Vue world is a solution called VueRx, which was built by Evan, which gives you possibility to have the streams as a properties. So instead of having static props which you change, you can have your props as a streams. So your entire component, not just some logic in the component, but actually entire component can be reactive. And this is really, really powerful. So thank you for listening, and hope to see your solutions in reactive world soon.